really tired. It's not my thing anyway. Actually, I don't want to take a picture of it. So I have to admit, this whole course is not actually my stuff. But I do like super fancy bioinformatics data structures. But I still like most of the, so I'm recording there, I'm recording. I really find most of the stuff in this course, and I have to start this. But most of the stuff in this course is like really fascinating to me. This last bit after the NP completeness, I teach this because the other professors insist that you have to know this. You have to, like Norbert says he wants people to know, I forget, I think it's Floyd Warshall or Bellman Ford or something like that. And it's like, really, why isn't Dijkstra good enough? So there, you'll see today that there are instances in which Dijkstra can't deal with it. But then, so there are cases like on sparse graphs, there are faster algorithms, but I don't think we're going to get to that today. On DAGs, there are faster algorithms. Probably not going to get to that today, but those are fairly easy algorithms. One on DAGs is any. So Bellman Ford is also fairly easy. So you'll remember from the last lecture, so Dijkstra's algorithm, you would, so you're the corrupt county planner who is going to arrange everything for their own convenience. And so you're going to pave the roads such that you can get from wherever you want to wherever you want as quickly as possible. And it doesn't matter if this costs the taxpayer extra money, and it doesn't matter if it's inconvenient for everyone else. They will still be able to get everywhere by paved roads because they can just travel from where they live to where you live and then follow the path you would take. So they would follow the path you would take from your place to their place in reverse, assuming it's an undirected graph. And then they would follow the path. So yeah, it's connected, but it's not minimum cost overall, and it's not minimizing the distance for everyone else. And also, Dijkstra's algorithm, from the proof of correctness, we remember it cannot deal with negative weight edges because we had this bit where you said, oh, okay, so you calculate the greedy proof. Oh well, if I marked a distance wrong, then I did it. It was one step away from the stuff I've marked correctly. Assuming up to step I, our solution is an optimal solution, blah blah. So we haven't made a mistake up to step I. On step I, this one we label the distance of the closest vertex that can be reached in one step. So where the distance to the vertex you would jump from, and then the edge cost is minimized. And then you can say, okay, but so then if you were to get to it another way, you would have to leave this stuff we've already correctly labeled. But that means that you would have to go from there to somebody who's one step away. And then that, by the way we're processing the vertices, is large. Wait, this has nothing to do with Dijkstra's. That's negative edge weights. And then you would have to say, okay, but then you've already gone further, or at least as far as our distance to this new vertex. But then what if you have a negative weight edge? And you could say, okay, but then I can, this distance is not 10, but in this distance, when I jump out by one step, it's 12. But then I have an edge weight with weight negative 9. So great. So today we see all pairs shortest path. Well, first we see how to deal with negative weight edges. Okay, we can't deal with negative weight cycles. At least you can sort of deal with a negative weight cycle in a graph if it's not reachable from your starting point. Oh no, it is recording. Okay, it's not reachable from your starting point, but we don't care, because that's actually not going to show up in this second, because it's not reachable from your starting point, and you're not going to find Okay, so what is Bellman for? It's actually sort of, it's more general than Dijkstra in that it can deal with negative weight edges, but it's sort of a slower, and like if you're really pessimistic and you didn't trust anything, you might run this. So what is it? Well, we'll see. So you start out and you say, oh, U W X, whatever. So okay, suppose we're starting at Z. So we say maybe this red is readable now. Okay, so the distance from Z to Z is 0. Okay, that's good so far. Now, what we're going to do, and initially we label all of these with distance infinity, which means this is an upper bound, right? It's not maybe the real distance. There's no way to get from Z to some vertex, and this distance is actually infinite. But this is just our upper bound, our estimate, which is possibly too high. Now, the idea behind this algorithm is, okay, if there is a shortest path, if there is no negative weight cycle, if there is a negative weight cycle that you can reach, then it's best to just keep going around it, because that means that the vertices on the other side, if you keep going around the negative weight cycle and then you come out and you go to those vertices, then you could have done that more cheaply if you'd gone around the cycle once more. Okay. So assuming there are no negative weight edges, does not mess with that. The shortest path now from Z to somewhere is going to consist of a finite number of vertices. Like you're going to start at Z and you're going to go somewhere and you're going to go somewhere and actually it's going to be at most n vertices. So the thing is, these vertices are not going to repeat. You're not going to have a loop, right? Because you wouldn't. Why would you put a loop in? It can have a weight at most 0, in which case you can ignore it. It can't have a negative weight by assumption. So there's always going to be a shortest path in which every vertex that you visit is visited once. With one Hamiltonian path, you don't visit every vertex once in this path, but any vertex you visit, it's visited at most once. Okay, so what we're going to do is sort of consider all of those paths, but in a slightly efficient way. It's sort of a bit like dynamic programming. So this means, so we're going to assume that every shortest path, where shortest doesn't mean the number of vertices, it means the total cost of the edges. Every shortest path is going to have length at most. It's going to have, okay, so it's going to have length at most n minus 1. Okay, because the length of, like if you have a vertex and an edge and another vertex is considered vertex, it has 2 vertices, but it's length 1. Okay, so that means, so we're going to run the algorithm at most n rounds. Okay, so at the end of the ith round, we want to maintain the invariant that everybody whose shortest path is at most I steps from Z is correctly labeled. And then by the end of it, you can say, okay, so everything at most n steps is correctly labeled. So because everything is within steps. So let's do this. Oh, right. And so we're going to do n rounds. And in each round, for every vertex and every edge leaving that vertex, you have some vertex U, and you have B1 and B2 and B3. Okay, and these are labeled with some distance, okay, possibly infinity. And if U is labeled with infinity, then, well, you can still do it, but it's kind of pointless. So what you're going to do is see, okay, so this edge we're going to see as cost 1, cost 2, cost 3. And what you do is for every vertex, you consider its outgoing, all of its outgoing edges. And you say, okay, so distance to B1, B1 equals min of V1, and then D. Oh, and so this is the distance at the current moment. So this is what we're updating it to, and this is the distance at the current moment. So it's like variables in C. It's not like this is I is equal to I plus 1. It doesn't make sense. In this case, it does. So du plus C1. Oh, that's not this. And then you want dv2. No, actually, that's dv1. No, that is, I didn't want to stop. Sorry. I guess I'm a bit zoned. Okay, in v2 is dv2 equals min dv2 du plus C2. Okay. D3. dv3 du plus. So for every vertex, so it may be that this is distance 5, and this is distance 2, and this is distance 6. In that case, we don't change it. Right? We only change it if this is distance 5, and this is distance 2, and this is distance 8. Then we say, oops, no, we found a cheaper way to get here than with cost 8. We found it with cost 7, so we say, nope, not 8 anymore. It's 7. So so there are n rounds. Okay, one for each, one for the maximum possible, one for each vertex and the maximum possible length chain. And then for each, so n rounds, for each round, we consider all the vertices and consider all of the edges leaving. Okay, and then, so let's see n square, just a second. So, yeah, it seems to be, doesn't seem to be that slow. Yeah, okay. So it says, yes, okay. Time. So this is Bellman Ford. Okay, yeah, it is only about as less than I thought. It's so for if we have n rounds, for each round, we're going to, at each vertex, we sweep all of the outgoing vertices. That's m. So it's going to be m times n. Okay, and the neat thing is, if you don't have a negative weight edge cycle, but you have a negative weight edge, this will find it. Okay. If it finds, oh right, and I have to tell you how at the end you detect if there's a negative weight edge, a negative weight cycle. So if there's a negative weight edge cycle, so after you do all of this, so you run this recursion for each vertex, and you run it as many times as sort of the depth. Okay, really tired. So how do you find out if there's a negative weight cycle? So what you do, so this works because you can see that eventually, so by induction, before you take any steps, Z is labeled correctly. After you take one step, everything whose shortest path is one step from Z is going to be correctly labeled because you've looked at Z and the shortest path is any other way to get here is going to be at least as long as the shortest path in one step. The path in one step, because we're assuming that these are the vertices we're considering ones that whose shortest paths are one step long. And so it's going to get replaced with the correct distance. And then after 2 steps, the things whose shortest paths from Z are of length at most 2 are labeled correctly, and so on. So after n steps, you're done. But what if it has a negative weight edge cycle? So then you think, okay, and what if there's a negative weight cycle? I need this. Okay, so you think if this has some, you have some distance labeling here, and then you think, okay, so if this is cost C1, this is cost W plus C1, this is cost C2, this is W plus C2. And you go around and you think, okay, if this actually added up to a negative number, so if the total weight of the cycle is a negative number, then you can't have the right label everywhere. So if you have the right label, then always this is going to be some, okay, this is going to be some W prime, and then this is going to be some C prime, and then this is going to be less than or equal to W prime plus C prime. Okay, but if you have a negative weight cycle, then when you go around, you can, if you go around often enough at least, well, but if you go around once, you've got to have the case that this end is going to be too big, right? Because assume that so if I start here, that if I go here, this is at most this weight plus this cost, okay, and this is at most this weight plus this cost, and this is at most this weight plus this cost, and so on until I get back to here. But then, if you take, it's like this weight is at most this plus this cost. This weight is at most this plus this cost. So that means that this is at most this plus this cost and this cost. Right? So you go around and you get back here, and it's like, okay, well then this weight is at most this plus all of these costs. If those costs are negative, you're getting that this weight has to be smaller than itself. So that means that if you have a negative weight cycle, then somewhere there's an edge where you've got U has weight 1, and this has weight C, and here you have V, and it has weight 2. But you're going to have W2 is greater than W1 plus C. So somewhere there's an edge where this doesn't, normally you have, if everything is worked out, you have the constraint that W1 plus C is bigger than or equal to W2. But if you've got a negative weighted cycle, then you can find an instance of this. So after you've done the n rounds, you just check all of the edges. Okay, any questions about it? Like I said, I'm not super on the ball today. Anybody still there? I have 11 students out of like 99 in the course. Okay, any questions about Bellman-Ford? That was easy, right? Maybe T will. Okay, so the next bit I do get a bit interested in because, okay, so like I said, if you have a graph that's a DAG, then you can topologically sort it, and you can find single source shortest distance faster. But we're not going to get into that. Did I start this? No. Maybe. Yes. Okay. So the next bit is this matrix multiplication stuff. So multiplication is in quotes because it's not exactly multiplication. It looks a lot like multiplication, but okay. Yes, I still have this graph. Pretty good. Oh, and this, so Bellman-Ford is a single source algorithm. You pick, in this case, you pick Z and you move around from the, and you find how to get to everything with the minimum cost from Z. The all pairs shortest path algorithms are computing simultaneously the shortest path between any two vertices in the graph. And this, I think, also works for negative edges, but nothing works for negative weight edge cycles. Negative weight cycles, really. So how would this work? So this is a bit like, we're going to see this sort of this idea again in a minute in flight worship. But the shortest path from A to B is either from A to B, okay, assuming no negative weight cycles, is either A to B or A and then some path to somewhere and then some path to B, right? So we can consider like, okay, if we know sort of the distance to all the possible intermediates, then we can sort of take two of these distances and glue them together and get the next round. Okay, I'll show you. So let's suppose we've decided that we're going to go from A to somewhere and then to B. And we want to figure out what's the shortest way to go from A to somewhere to B. Okay, so you would figure out, you would write a for loop, right? I wish we were in class. First of all, I wouldn't be this, I don't stay up late working when I have to actually be somewhere. And the bike ride would wake me up because it looks nice out. And I would be able to see you and ask you questions. So I would be making you do this. So I could sit down and drink tea. So you're trying to get from A to B. So the first thing you consider is go directly from A to B. And then to get from A to C and from C to B. So how would you, if you somehow knew the ways that you could do this in one step, right? You would say, oh, well, okay. For C in vertex class minus A minus B. I don't know if you actually have to. Okay. So you would say for all these C's, you want minimum of distance. Well, okay, sorry, you can write it. You would write it in a for loop if you're actually scanning. So, yeah. Distance AB. First, you set it to min. So here outside, you would say, okay, distance from A to B equals infinite. Then you would be, okay, min of the cost of AC plus, oh, what? Oh, I didn't hit the right button. Okay, I want to expect this. I'm just not having, oh no. Okay. It's not my day. Okay, so you can see that you would use a for loop, right? You'd be like, okay, for every way to consider this intermediate node C, I would go to, if I'm trying to figure out how to go from A to B with some number of steps, I consider all the ways to go from A to C with, so if I'm trying to take D steps from A to B, and I say, okay, for everything from 1 to D minus 1, I consider the shortest path with the most D steps to C, and then the shortest path with the remaining number of steps from C to B. Okay. So this is a for loop. So you'd say distance from A to B, we assume, okay, currently it's infinite, or actually maybe we have some estimate already. So for C, distance, more space, distance A to B equals min distance A to B plus min distance A to B in one step. So I'm going to put a 1 here. And this is going to be distance directly. Okay, so this is going to be like the cost of this thing plus distance A to C plus distance C to B. So this is the two ways that you can find this. You say, okay, either I go directly or I have an intermediate vertex. If I have an intermediate vertex, I sort of sum over all the ways, over all the choices of vertices and how I go there. Is anybody there? I'm not seeing any. Okay, so, okay, good. How would we do this? I mean, how would you implement this in a cool way? So let's do this because it's called matrix multiplication. Let's write a matrix. Let's get this right. So let's look here. This is UVW UVWXZ. So for U, we can go to this is UVWXZ, and maybe we say, okay, we can go from U to U from any vertex to itself with cost 0. We can go from U to V with cost 5. We can go from U to W with cost 8. We can go from U to X with cost -4. We cannot go from U to Z in one step. Okay. For V, we can go to U with -2. From V to W, we cannot go in one step. So it's infinite. From V to X, we cannot go in one step, so that's infinite. From V to Z, where is it? We cannot go in one step, so that's infinite. From W to U, we cannot go in one step. From W to V, we can go with -3. From W to X, we can go with 9. And from W to Z, we cannot go one step. X, I should have written this up before. X, we can go to Z with 2. X, we can go to V with 7. And this is infinite for the rest of them. And finally, for Z, we can go to U and W with 6 and 7. Z, and that's the only places we can go in one step. Okay, so we have this matrix. Now, how can we work out, thinking about that for loop, how can we work out easily what the shortest paths are using 2 steps? Okay, so I'm going to insist that now I want the lengths, the distances using exactly 2 steps. So what we can do is write the same matrix. -4. This is okay. So we write this up. Now, we think about, so if we're going from somewhere to somewhere else in 2 steps, we go from the somewhere to an intermediate vertex, and then so if we're going from W to X in 2 steps, okay, then we look at W to X. So we're going to look at all of the ways to go from W to somewhere. Well, let's say from W to Z. Yeah, because you can't normally get from W to Z. Just a double for loop. Sort of, but this is a nicer way to do it because this is going to tie back into matrix multiplication, and we've seen lots of tricks for matrix multiplication. It's not really matrix multiplication, but you'll see why it sort of is. So this is all of the ways to get from W to somewhere. And then what are the ways to get from somewhere to X, to Z? They're here. Oh no, Z is kind of boring because Z there's only one that you can get to. So where else? Yeah, let's say W to U. Okay. So we're trying to get from W to U. So these are all the costs of getting from somewhere to U. Okay. So how can we talk about the cost of getting from W to U in 2 steps? Well, if we try to go from W to U in 1 step and then go from U to U, it will be cost infinity. So, and I'm assuming you're allowed to stay at a vertex for 1 step. That's why I put these zeros. I forget if in the book it's infinite. I'm not allowed to do that. I'm saying you're allowed to do that. Okay, so it's going to be infinite plus 0. So that's if I try to go from W straight to U and then sit at U for the 2nd step. Okay, it's not exactly 2 steps. It is if you count sitting at U. If I go from W to V, right? So this is this and this. I sum this, and this is infinite. But then I take -3 and -2. That's a bit weird. But I can go from W to V in cost -3. And then I can go from V to U in cost -2. So I can go from U to, I can go from W to U with cost at most -5, right? Because I can W to U, I will go to V, yeah, -3 and then -2, -5. Okay, then I have a 0. I can go from W to W. I can stay at W. And then I can go from W to U with cost infinity. So it's 0 plus infinity. And then I can go from W to X and go from X to U. And that's cost 9 plus infinity. And then I can go from W to Z and Z to U, and that's infinity plus 6. Okay, so that's also kind of boring. But what do I put in the step? Now, notice this is not what we do for matrix multiplication. For matrix multiplication, these pluses are times. They're a dot, right? Because you take these 2 components. If I'm working across here, if I'm working across this row and down this row, then for each pair of components, for each pair of entries, I'm multiplying them, and then I add all of this. But now, if I want the shortest path in 2 steps from W to U, I'm going to take the sum of, for each way to go from W to somewhere and then somewhere to U, I'm going to take the sum of those 2 pieces, add them. That's the cost of that path. And then I'm going to take the min over all of these things. Right? So it's just, instead of taking where I normally take plus, where I normally take multiplication, I take plus, and where I take plus, I'm taking min. Right? Do people see that? Or do we want to see some more? Maybe. Maybe we want to do another one, another row. So let's consider going from X. So then we take a min of all of these things. And that tells us that the cost of going from W to U in 2 steps, allowing yourself to stand in the same place, actually it's at most 2 steps, is going to be, well, in this case, all of the rest of these things are going to be infinite, and this is going to be -5. Okay, so let's consider X. Let's consider how can we do this? Yeah, okay. Let's consider U to V. I wouldn't be opposed to, okay, good, because we're going to do, let's do U to V, because that's an interesting one. So U to V, we're going to do, but you see, the idea is it's just like matrix multiplication, but here instead of a sum, instead of a big sigma, I'm writing min, and in each of these, instead of a multiplication, I'm writing a sum, an addition. Okay, so let's say we're going to do U to V. The T is doing the go. I need to stop trying to hear. Okay, I didn't need to already stop. Okay, let's do U to V. Okay, so we can go from U to V, and then well, we can go from U to V and oh no, this is goes U to U. Okay, U goes to U. So U sits, we don't move. For the first step, we don't move. U goes to U, and then on the second step, U goes to V. Okay, so that is 0 plus 5. Okay, and then we can go U goes to W, which is 8, plus U goes to U goes to U, U goes to, oh, then this one is, oh, this is the, sorry, I forgot one. U goes to U, then U goes to V. U goes to V is 5. And then V goes to V, and V goes to V is 0. So what can we do in 2 steps? Like U can go to V and sit here, and sort of go 1, 2, or you can go 1, 2, doesn't matter. So now we're considering going to W with 1, 2. So U goes to W, U goes to W is an 8. And then W goes to V, it's a -3. Okay, so that's 5. So these two are actually the same, but we don't care because we don't actually. So okay, now U goes to X. And so if we were multiplying these things, you see, I would be doing this and it would be -4 times 7, but now it's -4 plus 7. And then finally, it's infinite and infinite. infinite, not 8. So now if I take the min over these, it's going to be this one. It's going to be 3. Okay. So the shortest path to get from U to V in at most 2 steps has length 3. Okay. So you can do a matrix, basically a matrix multiplication, where we can do the multiplication we know and love, and it's like cubic time. Okay. And this is simple and easy to remember. And maybe, I don't know, can you? I don't think. I wouldn't bet my life that you can do speedos like Strauss, because that's using the fact that you can add 2 matrices, and maybe that's going to change. Probably that's going to change if instead of addition you're working with min and so this is called min plus, I think. Yeah, so the normal one, the normal matrix multiplication is like addition multiplication, and this is min plus. So you can see, so how do you, if you want to work everything out in for 2 steps, it's going to take you like cubic, it's cubic time, which is like, oh, that's horrible, but cubic in the number of vertices. So, okay, how does that help? Like, if you want to find the shortest path, I told you about the shortest path has to have length equals to n. So now you're going to get something that's quartic, right? This n to the 4, which is horrible. How do you get this actually to work in practice? You use this trick called repeated squaring. So on the midterm, there was a question about counting paths. So this, you can also do these kinds of tricks for reachability, because you take the adjacency, instead of a cost matrix, you take the adjacency matrix and you multiply it and you square that. And this is going to tell you if you can get from some vertex to some vertex in exactly this many steps, or if you sum them together in at most this many steps. I will probably put this in the lecture notes when I actually get the lecture notes done. If I actually get the lecture notes done. So here you don't want to do the, if this is matrix M, then to compute the shortest paths of length 2, you take m times m. To compute the shortest paths of length 3 or less, it's m times m times m. Times being this weird min plus thing. And then for 4, it's m times m times m times m. But you can get that just by doing m times m and then squaring that. Right? So it's actually just 3 multiplications. And then if you want, so you can actually work out if you want. It doesn't matter, because if you go over, then if the shortest path has length 6, then if you're computing the shortest path of length at most 8 or 16 or something like that, it doesn't matter. It's still just going to be this. If it's at most 16, it's still going to give you the length of the shortest path of 6. So you just do repeated squaring. And how many times do you have to do that? You have to do it a logarithmic number of times, because the shortest path, as long as there are no negative weight cycles, the shortest path is always between any 2 vertices, is always of length at most n. Therefore, if you're sort of doubling the lengths, the maximum lengths each time, you have to do like log n squares. So ultimately, this is O of n cubed log n, which is like not too bad, sort of. No, it is. It's pretty bad. On a big graph, cubic is horrible. So, okay, I trust like people who are more awake than I am. Bellman-Ford is not hard, right? You're just going to say, okay, at each round, everybody for every edge, we check to see if the distance from the starting point to the one endpoint of the edge plus the cost of the edge is less than the distance to the other endpoint. If so, we update that, and then you just have to repeat that in. Okay, so Bellman-Ford is easy. This is a little bit cool. You know, you think, okay, that's neat. So like all of this stuff we have is optimized, not all of it, but maybe some of it. It's optimized for matrix multiplication. You can use here. Not all of it. Now let's, wow, we're actually getting through this really quickly. Maybe not. Okay, so Floyd-Warshall. This one I have to. So this is basically the same idea, but not exactly. So this you can get cubic time without this law. Okay. But it's very similar. It's still, this is matrix multiplication. Now it's going to be dynamic programming. So before, I was talking about distances. Now we're going to be talking, we're still going to, I was also talking about intermediate vertices. But now we're going to be considering intermediate vertices, and so one of the reasons I'm so sad, the solutions to midterm 2 are up, and I stayed up late doing those. So the Floyd-Warshall algorithm, it's different in the sense that instead of saying, oh, how can I get from here to here using at most this many steps like this, what we're going to do is say, we're going to consider how we can get from A to B using intermediate vertices up to K. So so imagine I'm trying to work out the distance from U to V, A to B, U to V, whatever. Okay, so distance U to V, but it's going to be this special K. Oh, now I'm hungry. So this is going to be the distance, but where no intermediate vertex is more than K. So everything is a number between say 1 and n, and this is recording. I'm just going to... Okay. So everything is between 1 and n, and we're going to say, okay, so we don't want to use any intermediate vertices larger than 13. So you can say, okay, so if I'm trying to consider the distance, so what's the shortest distance from U to V using intermediate vertices? At most up to 13. Well, There's always the option of I can just go straight from U to V. So let's say that this is cost UV. Okay, so that's just the edge cost. I don't have any intermediate. And then there is going to be the case that I'm actually going to go to vertex K, right? So that's going to be, I'm going to go from U to K, and then from K to V. But the cool thing is, because we can assume there are no loops here, because if it were a negative weight cycle, then it would be bad. And otherwise, if it's a non-negative weight cycle, then you can cut it and the cost either stays the same if it's a zero weight cycle, or it goes up. Sorry, it goes down. It goes down. If it's a positive weight cycle and you cut it, then the weight of the path goes down. Okay, what we consider is distance from U to K plus distance from K to V. But there's an important thing to consider. Because there's no loop, because you don't go to K and then wander around and come back to K, K can't be an intermediate vertex in this path. So this is K minus 1. And this is K minus 1. So this feels a little bit like the optimal binary search trees. Remember when you say, okay, we're going to work out this optimal subtrees up to a certain size. And then, so this is if we use K, and if we don't use K, then it's just distance K minus 1 from U to V. So if we're filling this out K by, if we're iterating on K, then by the time we're trying to fill in distances using intermediate vertices up to K, we already have this worked out, and we already have this worked out. Okay. Because if you start out and you say, okay, well, my smallest vertex is 1, and I'm going to think that, you know, I'm going to do this with K is equal to 0, it's just like, well, okay, you can only go directly. Otherwise, it's infinite. And then once you've got distance 1, you can say, okay, distance 2. So yeah, I guess we should write the code, and then we should do an example. And I should buy more coffee. Fortunately, we don't have another minute. We just have. I'm not actually late on assignments. Assignment 5 is posted. I have to write assignment 7. I would ask how people are feeling about the course, but I find people who show up to lectures are actually, you know, the most enthusiastic. So probably, even if you're not super happy, you're not as unhappy as the people who aren't here. Okay, let's write the code. So we know cost of going directly from U to V because that's given to us as the. So we do for K equals 1 to N, because the last vertex we need to consider, if we say, okay, we're going to use up to intermediate vertices up to N, that's saying we can use any intermediate vertices. And then we're going to say, oh, I think in the book they use ING, but I'm going to use for you. And then you have this recurrence. So this you have immediately. This, by the assumption, by the time we get to here, we have all of the stuff for k minus 1. I'm just going to check that this is actually, yeah. Oh no, what they have is they don't have this, but they have this in place. So this we can ignore, because if k is 0, then this is the cost of going directly. Okay, so this is now ugly. We have this space here. But okay, so we just plug this in. We have all of this, and for okay, this is constant time to compute this, is constant time to compute this. You have this stored. This is just an addition of two things you have stored. This is a min over two things, so it's all constant time. So this, how long does it take? It takes cubic time. So it takes O of n cubed. So it's a logarithmic factor faster than the matrix multiplication approach. But I think the matrix multiplication approach is cool because it's like two parts, like from way back at the beginning of the course. And then now at almost the end of the course, these things come together. Okay. We have 16 minutes. Whew. But I didn't really prepare anything else. I could let you go early if there's still anybody here. 9, I lost some people. Woot woot, you want to go early. Any updates about midterm 2 marks? No, because the markers can't start marking it until I give them the solution key. And I only wrote the solutions last night. So, but the solutions are posted. So it's, when I actually got into it, like I didn't program the stuff. I just sort of like, yeah, okay, I can. It's like, oh, I would do this, and then I actually sat down to code it. I realized, oh, this is why people were asking these questions. With the final cut, all material, everything, except probably it won't cover fast Fourier transforms. And it won't cover zero knowledge. And it won't cover fine-grained reductions. So you can skip, you don't have to study 2 lectures, which I just threw in there. So the problem with the final is they could, but yeah, I could make them do that next time. So for example, for the last question, I realized that it's not hard, but it's really annoying that I didn't say, usually on like competitions, the competitive programming, it'll say you're given n. The first line of the input is n. And then you can write a for loop and say, yeah, okay, fine, I'm gonna read it. So in this case, what you'd want to do is be like, oh, I get n, and then I set up either my adjacency list or I set up my adjacency matrix. In this case, I would use an adjacency matrix because you're gonna be iterating over everything anyway. And I realized, oh, that's so annoying. I didn't tell you you get n. So I had to like read this stuff into a linked list. And keep track of what was the largest vertex number I'd seen, and that was n. And then I had to read the stuff back from the list and then build the adjacency. And so, oh, why did I do that? I wasn't thinking. And so there was one thing where, so on the first question, I sort of knew this, but I didn't want to give it up because I told you, basically I told, in the example, I told you how to do it, right? I mean, I sort of gave you the dynamic with that little, with the figure of the DAG. But there's one thing I left out because, so I said that if you didn't catch this, if you just did the example and you wrote and you said, yeah, that'll work, and you didn't do this, then it doesn't take all the marks off, but it'll take 20% off, unless you have to normalize. Because if you just do what I did in the example you don't have any dead ends. You don't have anywhere where Ryan's going along and he gets to a town and he says, well, I want to take a red bus, and there are no red buses leaving that town. So he's stranded and forever. I mean, maybe he has red tickets later in his stack, but this is Ryan, so he doesn't think to look, he's just looking at the top of the stack. So some places, as long as you don't get stuck anywhere, the probability will sort of propagate down, and the sum of the probabilities on any level is 1. But if you get stuck, if Ryan gets stuck somewhere, then that sort of stays in that, at that level, and the weight doesn't propagate down. And so what happens when you get to the bottom level, you have to normalize. And I didn't put that in the example because I thought otherwise it would be too easy. But then afterwards I was thinking, oh, I wonder if anybody's going to get this. So I'm going to tell the markers it's only worth 20%. Is that like really evil? Should I? Because if I put it in the example, it would be super easy. If you want full marks, yes. If you want 80%, you can just ignore it and say like you just do the. Because in the question, it says you get the buses that he actually took. You get the colors of the buses he actually took. So it means he was successful. So all the ways, if you code the dynamic program that the example was telling you to do, it doesn't handle that case because that case doesn't come up in the example. So because if it did, then so without catching this, you can get 80%. If you catch this, then I'm impressed, and you get like 100% on that question. Was there any other really hard stuff? Did anybody still hear? If there's anybody still here, did anybody do the so when I actually sat down to go, it's actually really nice to code the stuff with instead of using sprintf to use doubly linked lists. And then there, it turns out in C, you can use pointers to pointers. So it's actually pointers to arrays, but so you have this star star. So yeah, I was like, I'm not actually, I haven't done this in a while. I'm not sure this is actually going to work, but it does, or at least it does on the Agata example. So yeah, C is cool. Like you can think, logically it should do this. If I do this and then you try it, it's like, wow, it actually does what you think it should do sometimes. Sometimes then it's surprising. But yeah, so the code for the bonus question was kind of weird looking. Yeah, that's so. I have a question. So people teach data structures with Java here. so I got taught data structures in Java, and I should turn the recording off, but I always thought it was, yeah. So I think that's standard. I'm teaching 2110 in the winter, and I want to teach it in C, because if you learn Java, it's like, yeah, it hides everything and it's like objects. But if you open up your computer, there aren't objects there. It's like, I had a friend, does anybody know this programming language, Alice? It's out of Carnegie Mellon. It's like animations. It's like a super souped up logo. And so I remember he was teaching people to program with, you have a dragon with wings and you can make the dragon flap its wings and stuff. It's like, there are no dragons inside your. If you open up your computer, like a pointer, actually sort of, you know what a pointer is. It's like 4 bytes and it's a memory address and it's actually there. That number corresponds to this position in memory, and that actually has a physical location. But objects, it's like, it gives you sort of a weird idea of what's happening inside your computer, which is fine. It's much safer not to use all this cool C tricks. But I think that to learn, you should, yeah, but that's like, you should, when you learn data structures, you should learn pointers. You should, like, I can post a link to Linus Torvalds. Linus Torvalds, I forget. Yeah, so there's he has a lecture where he says C is great because you're actually thinking about what the machine is doing. It's not trying to hide anything. Whereas Java is trying to hide stuff from you for your own good, which is great. Like, it's like you're in a car, and most people don't have to ever, I guess you do open the hood of your car, but it's getting rarer and rarer. Like, most people, the car is making a funny noise, you go straight to the mechanic. It doesn't simplify pointers. It hides pointers. And that makes it hard to think of some things. If you think about how the machine will do something, that's how you do it in C. And there are some things in, I'm gonna run out of time, but okay. So there are some things, I'm pretty sure that you would never think of these. So there's a data structure like Canute. So this is the best example I know of this. And I don't think this would, I mean, okay, it's Canute, so most people would never think. But I don't think you would think, anybody would think of it if they were thinking in Java. So the idea is you want to have a list of integers, and you want to be able to increment them, and you want to keep them ordered, and you want everything to happen in constant time. Okay, so like access is not, you have other problems. This is for like a, this is, he was doing adaptive coding. So this is where you're as you only make one pass over the string. So as you're going, you're coding with the slightly smooth distribution of the characters you've already seen. And then another character arrives and you encode it with the stuff with the distribution you've already seen. And then you update your tree because now that slightly changes the distribution. So this is the data structure for updating your tree. You don't need to know why you should have. But so the idea is you want to have all these nodes, and they're going to have integer values in them, and you want them sorted. And you want to be able to increment one and have it like jump to the right place in constant time. And so what you do, so this is, say this is 2, 3, 3, 3, 4, 4, 5. Okay. So, no, let's make this another 3. Okay, so what you do, everybody points to the leader of their group. So this, and it's a doubly linked list. Can people see this? So I was actually thinking, except for assignment 7, so I am super tired today, and this is not usually the stuff I do. Like whenever I need to know how to do shortest paths, I look it up. So I can never keep Bellman Ford and Floyd Warshall. I can never remember which one is which. So I was actually thinking of doing the lecture on diagonalization and computability, which is going to be the last one. I was going to ask you if I could do that today, because that one I can do in my sleep. This one I actually have to sort of remember the algorithms. But okay, so this is the kind of stuff I can also do this in my sleep. So if you want to increment this guy, then that's easy. You just cut it out of the doubly linked list. You have a pointer to the front here, and you insert it here. You increment you decrement the weight. Yeah, you're decrementing the weight, you're not incrementing. So you just move it to the front here and you insert it here. So that's fine, as long as you are not trying to decrement the weight of the leader of a group. Because if you're trying to decrement the weight here, everybody is pointing to this. So here, the only stuff pointing is like the doubly linked list. You can fix that in constant. So you can cut it out and move it. But if somebody's pointing to this, how do you move that? So does anybody see the trick? And this is what I think you wouldn't think of if you only know Java. So if you want to make this a 2, then so these have auxiliary data. This has some record. Okay, I'm out of time. Stuff like that. So what you want to do is increment this, but and Charlie. So what you do is you can't change all these pointers. There are too many, and they're not bidirectional anyway, so you can't even see them. So what you do is you take this and you swap the contents of memory. Can you swap the 2 and the 3? You can't swap. If these are objects, then all of these are pointing to this object. So you can't swap these positions. But you can swap them in memory. You take the contents of the memory and you say, okay, so here I have all of this stuff, and yes, you can just move the pointers around. Well, okay, so actually Bob is not actually going to move around. You have Bob and Eve. But now this 3 is going to be pointing this Bob. This is going to be pointing to Eve. So now you can change this to a 2. And now, because it's a doubly linked list and you know that you're right behind the front, you can take this out and move it to the front, and everything is constant time. So yeah, that's the trick. But that's not natural if you're only used to pointers, I think. Right? Because Java doesn't like you like reaching into an object and gutting it and pulling all the private data out. and stuffing it into another object of the same type, right? Like you're not in Java, it's like, oh, you have this object and this object, you want to swap them, then you don't think about them as like, you know, bits of memory, and like you reach in and grab and rip this 3 out of this and copy it into Java. Doesn't make you think like that. So I don't know. I mean, you came up with it. Maybe you do. Maybe you do see some Java, but that seems against the philosophy of Java. Whereas in C, it's completely natural. So I think it's best to learn C, and then if you don't like it, fine, use Java. But C teaches you what the machine is really doing. And Java, it's like another layer of, I mean, it's got the virtual machine, and like you don't, because it's hardware independent, whereas C, you really sort of think about, I just like designing algorithms. If I'm going to implement them in C, I actually implement them the way I think them up, whereas in Java, anyway. Okay, so that's a bit off topic. That's so I'll try to be more rested next time and be more coherent. Okay, people are probably gone anyway. Fine. I'm going to stop the recording. And so yeah, I'm going to ask to teach it in C, but I don't know if they're going to let me. This is the best example. I mean, yes, technically, of course, you can do anything you can do in C, you can do in Java. They're both Turing equivalent. So Turing complete. So that's I mean, you can always prove it by thinking, okay, well, you could always write a C compiler in Java, and then you can run your C code on your Java, so it doesn't matter. Like formally, it's not in Kolmogorov complexity, it doesn't even complexity that much, but the length of the programs, whatever. But I just find, so I wouldn't say that C is a perfect way of learning to think about like how the machine thinks. Because, for example, I don't program GPUs, but C doesn't make you think like a GPU. So I think if I were doing a lot of GPU programming, I'd want to learn a different language because, you know, that's more sort of like this piece stuff. I mean, what's the name of that giraffe thing? Hadoop. Hadoop is sort of. What about learning this in assembly? Could be, yeah, that's a bit too machine dependent. I mean, do you actually, the camera, do you actually learn assembly these days? I had to learn assembly a bit. I mean, but yikes. Cool. I mean, it's good to know how this, so, I mean, you can sort of see for C operations, you can sort of see how C is doing their operations, how you could take a C thing and write it in assembly. It's not like really nice, but once you know things about like how the recursion stack works and everything, you can sort of, C is not really. So I hope they let me teach it in C because I haven't used Java in ages. Okay, I am way over time, so I'm going to stop this here. Yeah, the lecture was a bit hit or miss. It's in the book, and I will write lecture notes about it. I tried to give slightly simpler explanations than what's in the book, but this particular chapter is pretty straightforward, also in the text. So if you have CLRS, good. So then Monday is network flows. So we have assignment 7 is on this shortest path stuff. Monday is network flows, and then Wednesday is our last normal class, and that's computability, diagonalization, computability, Kolmogorov complexity, halting problem. And then we're into review, and then just for the wrap up. We're almost done. Whoa! Okay, so cheers. See you Monday. And I hope maybe more people will come. Okay. Maybe they just didn't come, or maybe they're sort of tired. Okay, cheers.